So some secure files were sent to me in the search for fight against superbacteria. Let's do our part with chemistry. So first and foremost, we see a big bulky base, and when it comes to solvents, that is a polar aprotic. You'll tell it right there, the CH2CN. And so we actually want to start looking at our leaving group, in this case bromine, and next to it we have this hydrogens, right, in the beta carbons. And why is that important? Because we're going to actually want to look at the less substituted one. Yes, you heard me right. That's the Hoffman product we're going to be forming, the less substituted alkene. Now, we also got to look out for the anti-periplanar hydrogen, which is the most important part of all this entire reaction E2, because what you need is a hydrogen that is 180 degrees about that bromine. And what you'll come to notice that is critical is that when you have those big, bulky, strong bases, that, like in our case, those sp3 lone pairs in the oxygen, and that bulky terbutyl behind it, essentially what those lone pairs are going to do is go and deprotonate that hydrogen in a brown Celleria-like manner, attacking that sigma star behind, and those electrons that are left from the original connection to that carbon are actually going to make their way behind and attack the sigma star of the bromine, giving it its beautiful elimination name, in this case eliminating the bromine. Now when that happens, you want to make sure that those two sides stay in the same side. So that's really important for you to remember once you're done and you actually undergo that reaction with the curly arrows I'm showing there. And what you should be left with is something along the lines of this. And don't forget that fat lizards always stay still. But without further ado, while you look at that mnemonic, pause the video, we're going to go into Diels alders. Now, this is a tricky reaction, but what we're given here is actually a diene. And the molecule that we made is the one with dienophile. And there's two ways of attack, endo and exo. Now, please don't get confused with exothermic and endothermic. Both of them are exothermic. By exo and endo, we're really just referring to whether or not the group that is attached to the dienophile is pointing towards or not pointing towards our diene. And this actually results in some pretty interesting consequences. You see, originally, dienes are the only ones that have the conjugation. But once you add that group to the dienophile, what you end up having is actually conjugation in that new dienophile, and that actually results in a new interaction. You see, originally you would imagine that it would just be a Psi2 attacking a pi star, but now it's actually a Psi2 attacking a Psi3. That is our dienophile in conjugation, and this is the most convenient position. And why do we pick endo? Well, that's because of the secondary interaction that I'm about to draw right here. Yeah, you see that right. That interaction lowers the activation energy. Remember, this does not mean that the product is more stable. As a matter of fact, the exo is more stable. Instead, what it really tells us is that there's less energy required for that process to occur. So at lower temperatures, it does occur. And now remember as well that what we have here is an electron withdrawing group, which makes this homo-LUMO interaction better, right? That's why we have the Psi3, and that's why the HOMO can better attack the LUMO. Now, regarding Regis selectivity, there's also really important, which is the charges. Now, charges really do matter because that will depend on whether we attack flipping or not flipping our diene in respect to the dienophile. In this scenario, if we draw the resonance structures, we'll actually figure out that there's a partial positive in opposite directions to the partial negative. So we're actually going to have to flip to accomplish that Regis selectivity that it much desires. Now, it may come as a shock to you guys, but bears throw donuts perfectly, or at least they do when it comes to the stereochemistry of Diels alders. Below thumbs up, down, put them down. Let me explain. The thumbs are your inside groups, and your pinkies your outside group. The main idea here is that once you have your fingers stuck out, you're going to put those thumbs up, and that means the dienophile came from below. And if you put your thumbs down, that means the dienophile came from the top. But 99% of the time, it would come from below. And now, like I hinted priorly when I drew the exo and the endo with the little dashes above and the wedges, what we have to notice is that the groups that are from the dienophile and are pointing towards the diene, the endo, are going to be dashed. Whereas the ones that are pointing away are exo, and they're going to be wedged. In this case, we have the acyl group as the endo going down, we have the terbutyl going up as the exo group. Now we're hit with an aryl halide, right? We have that chlorine attached to a benzene ring, and we have a nucleophile. So this has got to be SNAR, or nucleophilic aromatic substitution. So what's going to happen here is essentially we're going to go on to form the Meisenheimer intermediate, and that's essentially just a tetrahedral intermediate that's going to go on to form. And because aromaticity is still stabilizing, that molecule is going to want to form it again. Now, it's really important to notice that where the electron density is going to the electro withdrawing group. And why? Why is it going there, you might be wondering? Well, it's all to do with its position. specifically the fact that it's para or ortho. Now, the para is really important because when that group comes in, it's actually going to be able to stabilize that charge. Meanwhile, if we have a meta position, it just won't happen. It will just be unable to actually complete and recuperate that aromaticity, or at least stabilize that complex, as you come to see here. Now, like many other organoreaction molecules, now we're going to be hit with osteonolysis and a reductive agent. Now, bringing it back to one of the main themes of organochemistry, we want to get those electron densities towards a positive charge. In this case, it can be more clear where we have our pi attacking our side 3. Why? Because there's an oxygen in the middle with a positive charge that is inductively sucking those electron densities away from our double bonded oxygen. So besides that pi side 3 main interaction, there's also a secondary interaction with the lone pairs of the oxygen, where it's actually side 2 attacking that pi star. Nonetheless, let's focus on the actual mechanism itself now. So you will notice that we are forming a molozonide intermediate. And another thing of our recurring class of chemistry is that electrons repel electrons, right? We know this. So this is extremely unstable. This bond is very, very unstable. So much so that it will just cleave itself in the following manner. To remember the mechanism, essentially going to be bond to atom, and atom to bond. Don't forget those arrows. A friend once told me this. Now we'll form this intermediate. Now it's when it gets interesting. Ozonide, the intermediate that we're looking at now, can actually be formed from the top or from the bottom. Why? Because while alkenes will always have that top or bottom addition. But what we're looking at is actually a diastereomere. You would imagine it's an enantiomer, being that both those chiral centers are opposite to each other. But in reality, we have other chiral centers, so it must be a diastereomere. That's something to watch out for, and it's something that's going to reoccur in our class. So it's just an interesting, but don't get too tripped out about that, because in reality what's going to end up happening is that those two chiral centers are actually just going to become sp2 carbons, so it doesn't really matter. Now what we're going to actually go into is the reduction mechanism. Now this is a little trippy, but I want you guys to stop and take a look at it. What we're really doing is just trying to move it around, and to make it more simple, there's a little skill I touch at the end. Honestly, this is memorization in my opinion. You can always just think about where the electrons have to go, but in reality the best tactic you can do is try to memorize this. If you can't memorize it, make your logic out of it. Why? How? Well, there's a simple trick, and that is wherever you see a double bond, wherever, and you're doing reduction, you're going to form that H there. Wherever you have a double bond and you're doing oxidation, you're going to form a, what is it? Oh yeah, a carboxylic acid. And yeah, that's essentially how it goes around it. And reduction and oxidation, well, you have to kind of memorize what it is, but usually oxidation is a H2O2, right? That's kind of like the main oxidative agent we use. So yeah, that's kind of a way to do it, and thank you so much for watching, guys. And the trick question for the beginning was an extra H in that third butyl.